Okay, I'm uploading it here.
That's good.
All right. I hope you have
Yes,
the
yes,
first
we
slide
do.
there.
Everybody can see it. Please start.
Okay.
Thank you.
All right. Hello, my dear colleagues and audiences. I'm Yashar. It's almost 2 a.m. here in Ottawa, Canada. I want to thank the ANZCC organization for giving us the chance to present our ideas here. This project is the result of the efforts of a group of researchers from Carleton University and the University of Ottawa, both in Ontario, Canada. I want to send my special thanks to my awesome team, Felix, Safi, Nahal, Shujeng, and Dr. Mohammed Atia. It's my honor to present this research on behalf of my colleagues. Okay, this study aims at introducing a novel equation for nonlinear least square algorithm for UWB positioning systems. The effectiveness of the proposed algorithm was verified experimentally. All right, what are the applications of positioning and why is this important? For industry, in case that you are dealing with autonomous machines in warehouses and wherever you need to monitor the moving objects. In rescue operations, for example, when firefighters enter a house that caught fire, they can communicate and find each other. This can be extended to various situations of underground operations, earthquakes, and so forth. In transportation, I'm pretty sure you all are familiar with the importance of positioning in transportation, so I'm not wasting time on this topic. And for smart homes, you may need to locate your items or imagine the front door unlocking automatically when you arrive home, or your vacuum cleaner starts moving around your house and cleaning floors and carpets. And of course, positioning has many other applications that cannot fit in this presentation. All right, why don't we use GPS for indoor applications? Two main drawbacks. The first one, GPS signal is weak and incapable of penetrating through objects. And the second one, its ranging accuracy is low and it degrades further due to multipath situations. Okay, multipath examples include atmospheric ducting, ionospheric reflection and refraction, reflection from water bodies, and terrestrial objects such as mountains and buildings. For example, like the figure we have here, the object that you want to locate is the star labeled target. Due to multipath situation and the reflections from the walls, considering the same angle and the same range, your anchor can detect your object at two different locations labeled Ghost 1 and Ghost 2. All right, what are the indoor positioning technologies? WLAN, or Wireless Local Area Network, that is generally used in smart homes. RFID, or radio frequency identification. Bluetooth, pseudo satellites, which are aircrafts that operate in the atmosphere at high altitudes for extended periods of time. It's generally used for military purposes. And UWB, or ultra wideband, that is the topic of this research. Okay, why UWB? First, it penetrates through objects and walls. Second, very high ranging accuracy, up to centimeters. Third, because of the high frequency, it less interferes with other signals. And last but not least, the low power consumption of UWB devices. All right. There are two main UWB technologies to estimate distance and location. The first one is shown on the left side, that is known as TOA, or time of arrival technique, and the second one is shown on the right hand, called AOA, or angle of arrival. All right, I'm pretty sure that you all are familiar with least squares technique. You use it where you are dealing with a lot of noisy measurements, and you need to approximate the solution of overdetermined systems by minimizing the sum of the squares of the residuals made in the results of every single equation. So in a case that the system is nonlinear and the number of the observations or the measurements is bigger than the number of the unknown parameters, the nonlinear least square technique provides the best approximation for the solution. Okay. In our case, we want to locate the position of a tag that is moving in a corridor which is monitored by 11 anchors, A1 to A11. The general least squares equation is y equals hx, in a way that y is our range measurements, Ri, x is the state matrix, and h is the transition matrix. Here on the left side, x plus is the optimal solution for the problem that minimizes y minus y plus squared, the error. As you see on the top, the range between the tag and each anchor can be found with the square root of the coordinates of each anchor minus the coordinates of the tag. This is a nonlinear equation, so we need to linearize it using the Taylor series around an operating point x bar. Okay. On the top, we have the Jacobian of the H matrix, and solving the H for the ith line yields the blue box that we see at the bottom of the page. There we have 1 over Ri, which the Ri itself is the square root of the coordinates of the anchors minus the coordinates of the tag. In the cases that the tag gets too close to the anchors, and considering some inaccurate and noisy measurements of the anchors, it is very probable that you get square root of 0 or something very close to the 0 in the denominator. Thus, dividing by the denominator results in a nan, not a number. Since these predictions are the basis for the next iterations of the algorithm, this nan can disrupt the existing knowledge of the system states for the future iterations. So we provided a simple modification for this equation to alleviate the problem and reducing the chances of getting nans in the predictions. We set the y matrix to be the square of the range data. In this situation, solving for the Jacobian of the H matrix results in the blue box that we see here. By this simple modification for the derivatives and the Jacobian of the transition matrix, we will not get nans. Okay, here you see the experimental setup of this study. We conducted the experiment in a 14 by 2.5 meters corridor, monitored by 11 anchors, arranged in a zigzag path. The UWB RTLS, real-time locating system device, used in this project is a Decawave DWM 1001 module. The measurement frequency is set to 10 Hertz. These units are equipped with UWB antenna and a 3-axis accelerometer as a motion sensor. The unit itself provides XYZ estimation for the location of the tag by fusing the ranging data of the UWB antenna and acceleration of the tag. In this study, we only used the range data of the UWB antennas and we ignored motion data. We analyzed the data and confirmed the algorithm on MATLAB platform. All right. Okay. Here we have the tracking performance of the nonlinear least square NLLS estimation in XYZ on the left and XY perspective of the same figure on the right hand. The blue line shows the built-in estimation of the device, which was validated with our own ground truth information, and the red line shows the NLLS estimations, nonlinear least square. This figure emphasizes that when the tag was very close to the anchors, the estimation performance was highly impacted. I should indicate that the number of nan estimates in the built-in algorithm of the device itself, is 45, and this number drops to 29 for the nonlinear least square algorithm. The next figure illustrates the distances between each estimation at each data point from its corresponding true value, and this deviation is defined as an error. Its mean is 47 centimeters in this case. All right. Here we developed another algorithm to produce true range measurements from the existing data sets. Then we compared the exact range measurements with what the decawave UWB unit had measured. This figure shows the absolute of the error in the range measurements of the UWB unit. As seen, there are errors even higher than 2 meters and up to 7 meters for some data points. Even there were situations that the anchors reported negative ranges, like -1 or -50 centimeters, -1 meter or -50 centimeters, that were completely incorrect and impossible, actually. This is the absolute of that error. Eventually, we decided to reconstruct the dataset using the mathematically verified true range data. Since in the dataset there were many nouns, we needed to interpolate those unknown data with a Savitzky-Golay filter with a linear least square regression and a polynomial model of a second data. All right. Here we repeated the algorithm with the reconstructed true range data. As seen, the proposed nonlinear least square shows an exact tracking performance when it is fed with accurate measurements. This figure shows the 3D distance between the estimates of the proposed NLLS algorithm and the built-in estimation algorithm of the UWB unit. The mean of the error is only 5 centimeters. It is notable that in this case, the estimates of our NLLS algorithm is more accurate than the device because it is fed with true range data. All right, to make it more challenging, we added a white Gaussian noise with a bias of 23 centimeters, exactly similar to the original data set. On top of the true, we added this on top of the true range measurements. All right. On the left, we see the tracking performance of the nonlinear least square algorithm, and on the right, we have the same results filtered with a moving average filter with a span of 2 centimeters. The span of the moving average filter is 2 centimeters. All right. It is observed that although we fed the same algorithm with a similar noisy data set to the original data set, the output seems to be more accurate. But why? All right. Here you see the single-dimensional tracking performance of the NLLS algorithm when it is fed with the original noisy data set on the left and the artificially manipulated and noisy data set on the right. It is seen on the right that the estimation has an error limited to a specific boundary, but on the left, for the original data set, in some intervals, the ranging noise was lower, and in some intervals, it has huge jumps, especially the same in the y coordinates. So we can conclude that when the error has not an even distribution around the true values, the estimation performance of the nonlinear least square algorithm will suffer greatly. All right. This chart provides a comparison for the number of nouns in each case. Fortunately, the proposed nonlinear least square algorithm was able to provide solutions for some of the data points that even the built-in estimation algorithm with the fusion of accelerometer data falls short of answering. All right, conclusion. This study aimed at providing an insight into real-time locating systems, introducing UWB and its applications, and presenting an alternative nonlinear least square solution for the positioning systems for the cases that the tag may get close to the anchors. We validated our proposal through an experiment and various data analysis techniques in different scenarios. We showed that it is better to place the anchors at points where the tag has no way of getting too close to the anchors. We suggest utilizing higher ranging frequency with the anchors to increase the number of measurements and reduce the estimation error. We also propose employing a technique that utilizes at least 4 and higher, an even higher number of anchors in each estimation, since the system becomes overdetermined and the error can drop further. We have 3 unknowns, x, y, and z, so at least 3 range data must exist for each data point. 4 and higher is more desirable. For future studies, we suggest investigating the effect of the arrangement of the anchors on the estimation accuracy, employing an extended Kalman filter, EKF, and fusing accelerometer data for obtaining better XYZ position, and conducting a comparative study between the performance of NLLS, EKF, and particle filter, PF. Okay, thank you so much for your attention. I'm Yashar, and I'd just like to emphasize the hard work of my dear colleagues, Felix, Safi, Nahal, Shujing, and dear Dr. Atia, and thank them. Thank you so much for your attention.
Thank you, Yashar, for a well-rounded and quite clear presentation. Much appreciated. Regarding timing, is just spot on. So do we have any question from session participants, please? Any question from session participants? If no, once again, thank you, Yashar, for presentation. And
Thank
could
you so
you
much.
now,
That was my honor.
yeah, could you please stop sharing your screen? Oh no, it's from here. Yeah, that's okay.
Yeah, that's on the
So
system.
that's
I think
fine.
it's control.
Yeah. Now, it was my understanding then